friend? I think I may have asked you the other day the incredibly personal question, did you ever have a crush on anybody? Could be that person in your kindergarten class who you just thought was adorable. You just wanted to sit by them. It could be somebody who, you know, you see at lunch. Whoever it is, I don't care. Cutie Pie! You just want to be next to Cutie Pie. Sorry, Kendra, I'm completely invading your personal space. You just want to be next to Cutie Pie. That is attraction. So, when you have protons in the nucleus of one atom, even though the atom's neutral overall, being attracted to electrons in another atom, that's an attractive force. That's an electrostatic force of attraction between opposite charges. But there's a problem. So let's say, okay, you got your image of Cutie Pie in mind. Whoever that Cutie Pie is, whoever it is who you just think is the absolute, what do they say, dog's ears, cat's pajamas, I don't know, owl's toenails, whatever. That person who you think is wonderful. Sadly, that person has a best friend. Have you ever met somebody who you just immediately could not stand? You just didn't want to be in the same room with them, the same car with them, the same lunch table with them. They just got on every last nerve you had. Yeah. Well, imagine, much to your dismay, that Cutie Pie's best friend is that person. Ugh. And Cutie Pie and best friend go everywhere together. Great. So you want to see Cutie Pie? Yes, I want to see Cutie Pie. Cutie Pie's awesome! You're going to have to deal with best friend. Hey, do you want to have a double date? Best friend and I can... So you are stuck trying to strike this balance between getting to spend time with Cutie Pie and having to maintain some level of distance from best friend. Cutie Pie! Best friend. It's this dance. It's a balance. And that's what's happening with electrons. So here's what I want you to imagine. You and Cutie Pie running across the field. Cue the violins and the fuzzy lens and the daisy petals. I don't know. Angels singing. Clouds parting. La, 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 la. And then, so you're running towards Cutie Pie and then, boom, up pops best friend. And it kind of stops the whole thing dead in its tracks. So there's this force of attraction, there's this motion toward, there's this momentum. But then suddenly there's this little wall, there's this thing that kind of gets hit. And you maintain a distance. I'm going to get, oh, okay, I'm going to stay right here. That's what's happening when you form a covalent bond. Remember, these things are sharing electrons. So we've got one atom that is attracted, the one nucleus of one atom that's attracted to the electrons in the other atom, because it needs those electrons. And we'll use carbon as an example. Carbon's a fantastic example. Okay, so carbon's got this positive nucleus right here, and I've drawn it badly, but it's got these regions of negative charge around it. They're actually hybridized orbitals, so we get 4 equal energy electron cloud bits. Not important yet, but we're going to talk about that later. So it's got these 4 negative things hanging off it. And along comes something like hydrogen, which is really not all that attracted to its own electron. It tends to be holding that fairly loosely, amazingly enough. Often it's found as just an ion. And hydrogen, it turns out, could very easily pop right in here and sort of complete that circle and make that electron cloud a more sort of continuous thing. And that's great. So we see hydrogen sort of aiming for the kiss. Going in for the best friend. Suddenly, that hydrogen nucleus starts to feel the repulsion from that carbon nucleus. suddenly those electrons on the hydrogen start to feel the repulsion from that electron cloud around the carbon. So how close do they get? They get to the point at which they are balanced, where you can still feel the pull. Everybody take your pencil. Try to balance it on your finger. I can't do it. Okay, can you balance something? Can you physically balance something? I cannot physically balance something. Clearly, some of you are pretty good. Clearly, I am pretty terrible. Some of you are not even trying. Eddie. Yes, you have to play my stupid reindeer games. I'm so sorry. Oh, okay. I apologize. Okay, you can do it. Sorry. You're much better than I am at this. That point of balance. So you feel how when you're trying to get it balanced, it wants to go one way, then it wants to go the other, it wants to go one way, and it wants to go the other, until finally it kind of centers. That's what we're talking about with this force of attraction and repulsion. It sort of wiggles one way, wiggles the other way, wiggles one way, wiggles the other way, until it finds a distance at which it's balancing the attraction and the repulsion. And then what we end up with are these, again, oh, yeah, wait, never mind, not so close. Charging in the force of attraction. Woo! Oh, whoa, okay, hold on. There's best friend. We'll do one more. Being pulled in, that force of attraction, again, between the positive nucleus of the hydrogen and the electrons on the carbon, getting about so close and realizing, whoa, that's close enough. That's close enough. So when we look at that in terms of energy, so the distance of the bond is the distance between the nuclei. The distance in radius is half the distance between nuclei of identically bonded atoms. And we're going to talk a lot about bond energy. Maybe I'll do it. I don't know that it'll happen, but I'd love to do a little tutorial on bond energy. That would be great. Don't bet the house on it. But we'll definitely talk about bond energy. If we look at I included this, especially for you visual learners. I'm one of you. If we think about that potential energy, when two things are running towards one another, when we've got those two atoms on a track to meet, think about two rocks rolling down a hill. They have a lot of energy. They're in motion. They are more stable when they hit the bottom of the hill. So if this is their energy prior to bonding and getting too close, well, here we go. Here's their energy prior to bonding. They get closer, closer, closer. There comes a point when they're at the lowest energy possible because they've balanced the forces. If they go too far and they get too close, suddenly their energy spikes because they're being pushed apart. That's where they settle on that bond length. So we're going to pick that up, well, apparently not tomorrow. And Friday you're going to do your lab. So boy, what a week. What a week, what a week. Have a good night, folks, and I'll have stuff for you on Classroom tomorrow.